Hey everybody, welcome back to the channel. In today's lecture, we are going to talk about dimensionality reduction using PCA, Principal Component Analysis. Let us understand what dimensionality reduction is. So, intuitively, dimensionality reduction would mean that transforming a high dimensional data space into a low dimensional data space or a feature space, right? It is done in such a manner that we preserve the most useful information. Its goal is to take out salient and informative features from the input data. To avoid any confusion, by dimensionality, here we mean the number of columns, input features, attributes, or variables. What are some of the techniques of dimensionality reduction? The primary techniques are PCA, Principal Component Analysis, backward feature elimination, and forward feature selection. Other techniques include missing value ratio, low variance filter, high correlation filter, UMAP, TSNE, etc. In this lecture, we are going to talk in detail about PCA, Principal Component Analysis. But before moving ahead, let us understand backward feature elimination and forward feature elimination. Backward forward feature elimination takes into account all the available features in the data and builds a model on top of it. It iteratively computes the score by eliminating one feature at a time and selects the best set of features. On the other hand, forward feature selection starts by picking up one feature and then goes on to add more features. Similarly, it creates a subset of features which are most useful or provide the most important information. Now let us go forward and understand the applications of dimensionality reduction. Till now, you must understand that dimensionality reduction is useful in transforming data space from high dimensionality to a low dimensionality. And where do we primarily see high dimensional data sets? Primarily in text based corpuses. Because of the huge vocabulary size, the dimensionality in text based problems are in general very high. The other application of dimensionality reduction is in feature extraction. When we want to extract features from the given data and we are not sure of which features would be the most useful. The third and the most intuitive application of dimensionality reduction in visualization. You would agree that it is always better to visualize something in a 2D Cartesian space as compared to an n-dimensional Cartesian space or even a three-dimensional Cartesian space, right? So let us move forward now and understand PCA, how it works, what are the different concepts around it, and understand what are the techniques of by which the PCA is computed: Eigen Value Decomposition and Singular Value Decomposition. So PCA is about using principal components, transforming the data into a new coordinate space where basis vectors constitute the axis of maximum variance in the data. Don't get confused with the jargons and the terminologies involved. Let me make it very clear. What are basis vectors? If you know or if you understand from Cartesian space the x and y axis, the x axis can be represented by the unit vector 1 comma 0 times the elongation or the scale by which we want to provide the magnitude of the vector. Similarly, y-axis can be represented as 0, comma 1. So these are the basis vectors which represent my Cartesian space in 2D. Principal component analysis tries to take this Euclidean space, these basis vectors, and create a new set of basis vectors such that the variance or of the data set represented along the basis vector is the maximum, okay, or maximal in this case. Now, from the figure, we can understand that there was a data set which is represented in a 3D Cartesian space. X, Y, and x1, x2, and x3 are the three axes. We are transforming it into a new 2D two-dimensional feature space where PC1 and PC2 are the basis vectors. We see that the variance of the dataset is maximum along PC1. The second highest variance is along PC2. So these two comprise our basis vectors with the maximum variance of the dataset. We should understand some of the concepts associated with principal component analysis to help us get into the detail of it. First and foremost concept is eigenvalue and eigenvectors. Now understand that matrix is a linear transformation. A matrix multiplication transforms the vector by rotating it or scaling it, right? Now imagine there is a vector such that upon the application of a linear transformation, its direction remains unchanged. Only its magnitude changes. So, such a vector corresponding to that linear transformation would be known as eigenvector, and the value corresponding to which the magnitude of the eigenvector changes would be the eigenvalue. So, for each linear transformation, we would have a corresponding eigenvalue, and corresponding to each eigenvalue, we would have a eigenvector, right? Now, how many eigenvalues can a linear transformation have? That would depend on the rank of the matrix. What is the rank of the matrix? The rank of the matrix is nothing but the dimensions along which the matrix would be represented in the Cartesian space. Okay. The another useful concept is covariance matrix. We understand from covariance that covariance, the diagonal elements of covariance represent the variance between the same data points, between I and I, the variance. Whereas the non-diagonal elements represent the covariance between the ith element and the jth element. The I and j depends on the row and column indexes. Okay. Covariance matrix can also comprise of two terminologies, spread and orientation. Spread represents the variance, that is the left or the major diagonal, whereas orientation is represented as covariance. Okay. Eigen decomposition. Now, using the concept of covariance matrix, eigenvalue, eigenvector, we know that PCA can be computed using eigen decomposition. So, what is eigen decomposition? It is the factorization of a matrix into a canonical form, whereby the matrix is represented in terms of eigenvalues and eigenvectors. Very simple. We are taking a matrix, we are transforming the matrix using the set of eigenvalues and eigenvectors. Here we have the computation of a matrix in by eigen decomposition. So first of all, we see a matrix A with its column vectors 5, 2, 4, 2, 5, minus 1, and 0, 0, 4. Now using eigenvalue decomposition, what we try to the way eigenvalue decomposition works is we take A, the matrix, multiplied by a vector, which would be equal to the scalar multiple of that vector. So A V is equals to lambda V. Lambda is a scalar. Now V is the eigenvector corresponding to the eigenvalue lambda. Using the computation, the mathematical computation, as we can see in the image, we would have three eigenvalues at the end of the computation, which are 4, 3, and 7. How this computation takes place can be understood by using reading any of the textbooks or through some of the mathematical concepts that you would be aware of using matrices. But just to understand the gist of it, how PCA works, understand that using the matrix A, we come to three eigenvalues. Now the eigenvalues, okay. Now sorting we sort the eigenvalues in descending order. Now it would be 7, 4, and 3. We compute the eigenvectors corresponding to each eigenvalue. Here we would have three eigenvectors corresponding to the three eigenvalues, which would be 1, 1, 1, 0, 0, 1, and minus 1, 1, 5. These are the three vectors. So after all the computation, we would come to the final equation of the matrix A would be eigen decomposed into vector V. Matrix V. Matrix V now represents the eigenvectors. This sigma is the matrix denoting the eigenvalues, which we can see here. And again, V inverse is the same matrix V with its inverse. So now let's connect back the dots. We understood what eigenvalue eigenvectors are. We understood eigenvalue decomposition, covariance matrix. Now the objective of the covariance matrix is to represent the variance and the covariances of the data points. Now if you have to represent that covariance matrix using a vector, so intuitively you would select that vector which is representing the maximum variance for that covariance matrix, which is able to contain the maximum useful information, right? So similarly, what PCA tries to do is it tries to map the variance in its data points to the to a Cartesian space, to a newly transformed feature space, such that the basis vectors constitute the maximum variance. Okay. Let us now summarize what we have learned so far. Given a data matrix of dimensionality n, we mean center the matrix, we subtract each of the values by the mean of the attributes. Next, we compute the covariance matrix. We decompose the covariance matrix into eigenvalues and eigenvectors. We select the top k eigenvalues. Because we are to reduce the dimensionality n to dimensionality k, we select top k eigenvalues and their corresponding eigenvectors. Now, k denotes the dimensionality of the transform representation. Now, using the matrix representing k eigenvectors, the matrix we saw in the last image, we transform the original data matrix and constitute a new data matrix with the dimensionality with the same m cross k. Hope you understand PCA in detail and have a great understanding of what PCA is, how it works, and the mathematical intuition behind PCA. Next, we talk about singular value decomposition. In our last lecture about topic modeling, we already discussed about singular value decomposition in brief. Here we would try to relate singular value decomposition with our eigenvalue decomposition. So singular value decomposition is a generalized case of eigenvalue decomposition. While eigenvalue decomposition requires square matrices, singular value decomposition can work with all kinds of matrices. When the input data matrix is symmetric, SVD becomes equal to eigen decomposition. Hope you enjoyed the lecture. See you in the next lecture. Bye bye. Have a nice day. Thank you. And don't forget to subscribe to the channel.